All right, in this last tutorial, what we're going to do is we're going to talk about functional inverses and how to find their values and also how to find the inverses of some more harder functions that are one-to-one. Okay, going through some algebra. Okay, so here we go. First off, quick review in applying this concept. We've said before that if we have a function composed of its inverse, you can switch it around in any way you want, that it should equal x. That is how you know, all right, that's the test to find out if functions are inverse of each other or not. Well, if I have a function over here, and it's inverse, right there, and I'm asking you, okay, if I composed f composed of its inverse, which is the cube root of x minus 5, you went through that process, you would realize that this would equal x, and it would equal x. We've done this several times. Where students sometimes get a little confused is that now they, instead of having x, we actually plug in a number. So if I had the inverse of 3, and for some of you might know the answer already, this should equal 3. It should equal the input. Now, just to verify this, let's just go through the process. I plug in 3 into here. What I should have then is negative 2, the cube root of negative 2. And that's going to be of f. So I found this. I plugged it into the inverse first. So I plugged it in right here. And then I took this, and now I'm going to actually take that value and take the cube root of negative 2, and I'm going to cube it, and which gives me negative 2 plus 5, which gives me 3. So I verified what we knew about these inverses. Now you can go through that process for all the other ones. However, if you have a function, or in this case the inverse, composed of its function, so it doesn't matter which order you go in, whatever you have, it should equal the input. So in this case, it should equal negative 6. Just to verify, let's try this way. Plug this in here. All right. We'll have negative 6, and that's going to be cubed. I'm not sure what all that cubed is, so I'll just put it like this. Then I plug that in right here into the function itself. So I have this minus 5, and take the cube root. And what you realize is that these will cancel out. I'm left with this, which is negative 6 is my answer. Once again, verifying what I already knew. This can be applied in a range of different values. If I have a function composed of its inverse, and I plugged in pi into here, my value is going to be equal pi. If I had f, the inverse of f, composed of its inverse, right here, and I plugged in elephants. You can't really plug in elephants into a function, but if I did, and I plugged into its inverse, I would get out a bunch of elephants. That's what I would have. Okay? But whatever goes inside for your input, that's what comes out. A function composed of its inverse equals the value of the input inside. All right. Now I went through here. We're going to go through some additional problems dealing with inverses of how to find inverses of functions. Okay? So for this next one, we're going to take the square root of 16 minus x squared. Now, if you're not familiar with this, this is actually a semicircle with a radius of 4. Okay, you can put this in your graphing calculator, which I did prior. Y equals here. You can punch it in here, and you can graph it, and we have this graph. Now, for these right here, if you don't know what they should look like, but for this graph by itself, you probably want to put in your graphing calculator. Finish my thought right here. And now we're going to look at this and say, okay, this graph by itself does not have an inverse because it doesn't pass the horizontal line test. Okay, remember the horizontal line test. So we need to restrict this. And that is why they give us this portion right here. I gave you this portion. So we're only going to take this graph from negative 4 to 0. So this is the graph I'm using. Now, with that knowledge, if we were to make another graph of the inverse, and make this in green, knowing this has to be symmetrical over y equals x, and now I'm just like thinking, all right, it's y equals x. It appears that my graph would probably have to be like this, like so. All right, going over 4, probably something like that. Okay, that would have its symmetry. Well, let's verify what we have here. So let's go through the process of finding this. Switch x 16 minus x squared. And what we have right here, then, we're going to switch x and y's. We have x equals the square root of 16 minus x squared. Oops, minus x squared. And now I'm going to solve for this. I'm going to square both sides. We have x squared. And that's going to equal negative x squared right there. We have negative x squared equals, oops, what did I just do? That should be y. I apologize if you were confused. Really do apologize about that. And then we take the square root. Now, when you take the square root, I messed up this entirely. Holy moly. All right, x squared minus 16 and that equals negative y squared. Take the negative, and now we have 16 minus x squared, and that equals y squared. I apologize. And now we have plus or minus the square root of 16 minus x squared. And that's our value. Now, that is a complete circle, because when you take the square root, you get a plus or minus. Now, the question is, are we using the positive or negative? That's why looking at the graph can kind of help you out. It can also help you out by looking at the original function's domain. If this is domain, that means the range should be from -4 to 0 for your inverse. Remember, everything is switched. The domain of the function, domain of f, equals or is equivalent to the range of its inverse. So with this, knowing that I'm going to negatives, I'm going to have a negative portion right here. Right there. Now the next thing is, now that I know the range, which is going to be down here, I know that I have to restrict that. Well, the restriction I'm going to place upon it is what I know. All right, looking over here, we know that the domain and the range here is going from 0 to 4. So the range of this function, f is range, is going from 0 to 4. So that's what we have here. So that means that's going to be this domain. So my domain for this function is going to be from 0 to 4. Because once again, everything is switched. We can also identify that by looking at a graph and creating this, putting it beforehand. We can see that we can already restrict it from 0 to 4. Either way, we have our function inverse that needs a restriction by looking at domain and range and also the graph itself. Well, we'll go through one more, this function. And the function I don't have up here, but I'm going to write out. And this one we're going to be using is, we have f right here, and we're going to have x plus 3 over x plus 1. Now, when we graph this one, and whenever you have tougher ones like this, I would really strongly recommend graphing them. And I have this one already set. We graph this one here. And we have here, and we have an asymptotes, and we have a vertical and horizontal. But looking at this, does it pass the vertical line test and horizontal? Yes, it does. This right here, it appears at 1, which there is 1. This is a horizontal line, so technically there are no values there. This is a horizontal asymptote at y equals 1, so never reach the graph, but so the horizontal line test does work out for that. So knowing that this passes the horizontal line test, what we can do next is we can find its inverse. All right? By finding this inverse, we're going to go through the same process. Y equals x plus 3 over x plus 1. And now we're going to switch the x and y values. Now this is where, make sure you do that, unlike the previous problem I had. All right? From here, this is where students sometimes get a little confused. How do you solve a problem like this? Well, the algebra steps to now solve for y, now we're solving for y, is I'm going to get rid of the denominator. So I'm going to multiply both sides by y plus 1. When we do that, I'm going to distribute that through, and we have xy plus x equals, these will cancel out, y plus 3. Now from here, I'm going to get all the y functions and the x functions on one side. So I'm going to subtract the xy to over here, xy, and I have plus y. I'm going to take that 3 and put it on the other side, and that's something like this. From here, I now notice that I have 2 y values. I like to sing a song, one of these things just like the other. What can I factor out? The y. When I factor out y, I have negative x left over, and this turns into positive 1. I can now divide by negative x plus 1, and that is my function. And that's my inverse. No restrictions needed. That is simply the value. Just to verify that this works out, I'm going to y equals, I'm going to delete that one from the previous one. I'm going to punch in x minus 3 divided by negative x, right, plus 1. And hopefully everything works out. I graph it. And I believe it does. Because if you look at this, we do have symmetry with the y equals x line right along here, where the blue graph, all right, is our inverse. Let's write that in blue. Blue graph is our inverse, and the red graph is our original function. So these values right here will be switched over here and be right there. And these values right here should be, the blue, should be corresponding to those over here, and we do have that symmetry. And we found our value. So we went through 1, 2 varied problems on how to find the inverse of some harder different functions. We also talked about the properties of inverses and how to solve when you have a function composed of an inverse. Hope this helps you out on finding your inverse. Good luck, and God bless.